Alright, so moving on with some live C coding, and in this video I'm going to be implementing the driver for these two shift registers on the schematic. They are located here. Let's see. So they are right here, and they've got a few switches connected to them and several control signals. We're going to start by defining, actually I think I already have the SPI device defined in my device tree. So let's open up the device tree. We have the device tree here, and we've got the SPI3, which is connected to both of the chips. And the only thing we need to do beyond that is to define the GPIO pins for the chip selects. So let's go ahead and do that. Let's see. I can do it as part of the SPI block. It doesn't matter where this goes because this will just be referenced from the driver of each chip. But I think it makes sense to structure the device tree in a hierarchical manner, so that you don't have to search for some part of the device tree like among all the other different definitions. So I'm going to put the pins here. This would be SPI3 CS pins, and it's going to be compatible with STM32 GPIO, and this will be pin control, and we're going to have something similar to this, except it's going to be just outputs. So let's see which pins belong to this. Let's see, GPIO. So we got PG3, and we have, I think, GPIO-X. Let's see. Or is it GPIO-X? What is it called? GPX CS. Oh, yeah, it's right there. So PG15 and PG3. So let's define these two. GPIO-G, GPIO pin 15, and this would be GPIO mode out. Now we have GPIO-G. We can also actually define the reset pin for both of them. Well, let's do this first. So GPIO pin, pin 3, GPIO mode out, and then GPIO-G, GPIO pin. So reset for the first chip is on PG4, and there's also interrupts for this chips. But I'll handle that a bit later. First of all, I want to just get some output from the chips. And I think we probably need pull-up, but for now I'll just make them outputs. Just get something simple running. Let's see, where is the other reset? this one is on PD3. So 3 GPIO mode out, and this would be GPIO D. So see how practical this is. So this will go. This will be loaded in generic code that goes into the GPIO driver. So the only thing that I need to do to implement this kind of flexibility is just to write this GPIO driver that implements generic GPIO, and then this driver configures the pins based on the device tree. So it's just this code, and this gets reused for every single instance of the GPIO driver, for every single node that uses GPIOs. So I'm very happy with this solution. I think it's fantastic. It's very flexible to write generic code and then define everything else in the device tree. Anyway, so now I will add some nodes here. So this will use the SPI3 node. So it needs to come after the SPI3 node, so that we have the SPI3 node already defined. And let's call this one GPIO. GPIO. Actually, we can call this GPIO 1 and GPIO 2. This will be compatible with our new driver. Let's call it mcp2317. Actually 2317, or no, actually S17, yes, because it's an SPI driver. I changed my mind again. I'm going to call it 2317, and then I can implement both SPI and I2C if necessary in the future in the same driver. So mcp2317. And then we go to define the pins here. So this would be, this will have a SPI pointer, which will point to SPI3. And then we'll have GPIO, which would be SPI3 control pins, I guess. Let's call it control pins. Because it's not just CX pins, it's reset as well. And I need to add a label here so that I can reference it. Be labeled like that, and then the GPIO2. Let's see. And the CS will be, and now we can define the different pins. So we can call this actually CS pin, and this will be indexed into the array above. So in fact, we can just add some comments here to specify what this is. So G15 was, I think, GPX. Let's make sure. G15. Yeah, it's GPX. This will be GPIO, and 4, CPG4 is GPIO reset. And this would be 3, that would be the other reset. GPX reset. So CS pin, yeah, and GPIO1 is the GPIO, whereas GPIO2 is the GPX. CS pin is contact. So this would be number 1, and this will be number 0. And we can take reset pin, the, let's see, GPX reset, so 1, 2, 3, and this will be reset pin equals 2. Alright, so we got a basic structure here, and the only thing that remains is to add this actual driver to the code base and make sure that it loads so that it gets called for these nodes. Our GPIOs are already going to be available. So let's add a new driver here. I'm gonna add this to lib driver because this is a generic driver. This can work on any architecture, so I'm going to put it into lib driver. Let's see, and it will be a GPIO driver. Let's add a new directory for GPIO. Just getting some quick boilerplate. We'll have, we need to include the driver definition, the FDT, yeah, and a few other files as well. So I'm just going to copy this. Let's see, we can copy, yeah, we can include URL as well. Chip, types, we don't need order, serial, console, yeah, we don't need console. And uni std arg, don't need that, we don't need math. I think that's pretty basic. Includes, and we can also remove that one. So types are not necessary. Then we have the let's see, mcp2317 probe, FDT, and FDT node. So this is how I chose to add device tree to my code base. I base everything on the macro that actually puts this driver into a list of all drivers that are compiled into the firmware, so that the code that loads the device tree can then go through this list and add and probe all the drivers based on their compatible string. So that's pretty much what happens. So this is the compatible string, and then we have mcp2317 probe and mcp2317 remove. and then we are not putting any semicolon after that. Return 0. Come, enter. And then we need to retrieve the SPI. So int, this would be, actually I'm going to be, let's see, I'm going to see if I can place that, that code into some function that makes it much easier to use that code. So basically we need to find the node from the reference, and then we need to retrieve the device. I think it will make sense to just place a utility method. So this will go to SPI H, and actually SPI C as well. Let's see. Right, so this will be just SPI device, SPI find from ref. T. No, actually, let's see. Shall it be? Yeah. So this will be the node inside which we're going to search, and then const char ref name. And now we can just place this code here. FTT node, and then ref name. Return 0 if it was found. I'm going to return end if the node is actually not found. If the device is not found, so if there was some problem with the driver that the device did not register, then we're going to return not found. And otherwise, yes, of course, we're going to return the device in this case. So, yeah, that should be it. I'm going to just place this into SPI H. Find by ref, and then we have here SPI device T SPI equals SPI, find by ref MQT node and SPI. Great. If not SPI, then we'll print K an error saying that mcp2317 SPI not yeah. Probably I should return the error code so I can actually print the error. I'll have a think about that. Okay. And then we need to do the same thing for the GPIO. So this subsystem code would probably need to be templated. If this was C++, that would be a template, definitely. In C, that would have to be a set of macros that define those methods. Let's see. And then we have CS pin equals T get int or default. And then we have the T node, CS pin, and default. Default would be actually 0, or actually -1. No, actually it would be 0 because the default is to use the first pin that is defined in the GPIO definition. And the same thing for the reset pin. Then we should be able to start. Let's see if we can read out something from the chip, such as some kind of identification code, just to make sure that the chip is working. So this is a datasheet for the chip. This is the registers, and it's quite probable that maybe there is no identification code or anything like that. So we'll need to just probably we can just read like direction registers and make sure that we get the defaults for them. Let's write a simple console command that will dump the registers of this chip. And now we can add it. Now that I've added the console driver and made sure that it's generic, now I can just easily add commands to other device drivers that help debug the device that I'm working on. So I'm gonna add a new command here, which will be, let's see. Actually, I'm gonna do like this. First, I need to add the GPIO method for finding by ref, and this is just gonna be a copy paste from the SPI. Just the only difference is that it will return GPIO twice. Okay. And this will just print a ready message into console. So you can see the console in this window here. This is what the console output looks like. I try to keep the strings as small as possible because I don't want to waste any flash space for very long strings. In this case, it doesn't matter because we have a lot of flash. For a smaller chip, it does matter because, for example, if this runs on an STM32-103 with 64 or 128K flash, then strings, having a lot of different strings, does add up to the flash. So I try to keep those messages very short. So what we can do now is just allocate our device. So this will be struct mcp2317. I call it self because this is going to be the object we are going to be creating, which represents this driver, and kzmalloc size of struct mcp2317. And this will actually be a GPIO device. So it will implement the same interface as the STM32 GPIO, and it will be usable in other drivers just like any other GPIO device. So I will define a GPIO device dev, and then I will also add the variables for every interface here. So we have SPI, we have GPIO device, GPIO, and we have int. This could actually be like uint8. Let's make it 32 for now. CS pin, reset pin. And then we need to initialize the GPIO with appropriate methods for setting and toggling pins. So let's see. We have three ops that we need to implement for a GPIO driver. It's set, reset, and read. And actually read is just a utility function. So write pin and read pin. This is the two we're going to be implementing. Let's call it mcp2317. So be static. mcp2317. Static. And static struct mcp actually GPIO device ops mcp2317 ops. And then I can initialize this device with GPIO in it self dev and mcp2317. Oops. And GPIO register self dev. So after doing this, we'll have a GPIO device available, which will have the same name as the full path to this device tree node. Let's update the GPIO init as well. Oh, this really changes the API. But yeah, I should have done this before. I should have. Oh no, that's here. I should have specified both the FDT and the FDT node. So this will create some compilation errors. So I'm going to continue writing the code, and then I'll try compiling this and fix all the errors. Okay. And in this case, we don't need to have a separate driver for the console commands, because in the case of the CPU, that has to be the first section in the device tree, because it sets up the clocks and it does a job that's important for many other drivers. So in that case, I had to have a separation between the CPU info and the main driver. But in this case, I don't need to have that, because I can have the console fairly close to the top of the device tree, and then I can, as long as I can reference the console from this driver and the console has already been initialized, I can just do the installation of the commands from the main probe method here inside this driver here. So I'll just add the commands here. Let's see. So also I'll just get the console pointer here. Let's see. Console. And I can actually put it here, and then only initialize this if console is specified. So console add command con, and then we need to specify the name. So this will be mcp2317. However, I need to specify the name based on the instance of this driver. So because we can have several mcp2317s, so we naturally want to have different console commands for each one. So I'm wondering what would be the best way to do this. I think it would be reasonable actually to create a variable here. Let's put it here. So this would be char name. We can make this like 32 bytes and do sn printf into name and mcp2317 let's see. Or maybe I could actually use the name of the node. Let me think here. Actually, I will use a variable instead. So this will be all of the probe methods are going to be called from the same thread, so we don't need to worry about any synchronization here. And then we can just make this name. And finally the method. So this would be mcp2317. CMD. And I'm going to rewrite the macro to actually allocate the command definition structure and copy all of this text, like both the name and the description and any options. It has to be copied into that structure. Let's see. Only then can we use a dynamic name. Damn, this is completely unnecessary. So console command init is actually going to be called from the console add command. It sounds reasonable. So let's actually rename this one to add command. Name, description, options, and the function. And then this can be removed. I should have called that one con printf anyway. It's not a name. is too long. Anyway, console add command. Console C. This will be like this. And console add command. Console. And now instead of just assigning the pointer for the name, I will allocate the name like this. Yeah, we can use a share copy here. So self name, and then the same thing for the description. And then we just call the dev, so like this. So, con command con So going back to the MCP driver, this will be added here. Console add command con name MCP utilities and the CMD. And now I need to just add this method. So it's going to be static int mcp2317 CMD. This will receive console pointer. So I just realized somehow I need to get the pointer to the instance of this driver here as well. So So now that we have a lot of different drivers that can use the same console to output messages, one of the things we need to do obviously is to make sure that the console is thread safe, so that different processes can use it without any worries about synchronization. But there's also another issue here that the virtual method for the command only knows about the console. So essentially, this will point to the dev ops variable inside the console object. So I think we do need to supply this. We do need to supply an extra pointer to the command object, because there is simply no other way to retrieve the pointer to the particular instance of this driver otherwise. So we're going to add a pointer to self here. And unfortunately, this will have to be a void pointer. Unless of course I have the console command variables defined inside the mcp2317 object. In that case, I could have used the more preferable way of using the container off to get the pointer. But in this case, there's simply no other way to do this in a simple manner. So console add command is going to also accept user PTR. And the command also needs to have void user PTR. Yeah. And this changes several interfaces. So one of the things is that we're going to add user PTR here. But also I will need to update other code that uses this interface. So the CPU code will also need to update the pointer there. Hello, Rashad. Okay. And then here I can place the code for reading out the registers. So let's actually just do a console printf. And then I'll see if I get both commands registered. That will be the first step. So going to the device tree, I will just check if I need to add anything here. So console equals console. So console goes there. Both go to the same console, and let's see if we can compile this. we're not going to be able to compile this, I know for sure. Conflicting types for console command. Console add command. Yeah, of course. So user PTR, and then self user PTR is going to be user PTR, and then also when it calls the method. Oh damn! Let's see. Yeah. Okay. Yeah. This will need to be also added to console C, which is a specific implementation of the console, but in the method that calls the actual function, let's see, where is it? Let's see where it calls proc. Yeah, here. So this will also pass self dev. No, actually, no. This will pass CMD user PTR. Awesome. So like that. Right. And this will need to be updated to also include the user PTR. Right, okay. Let's return 0 here, actually. So we're returning the pointer. So that's entirely correct. The same thing here. Let's see. Okay, console command init, implicit declaration of console command init. In this case, we'll just do console add command. Con self, or actually null in this case, because there is no object for this driver. And we can simplify this one then as well. So console add command con null. That's it. Passing argument 6 and compatible. Right. Also the implementation of the methods need to be updated with void user ptr. Same thing here. Going forward to the GPIO device init. This will need to have the FDT, so pointer to the device tree, and then GPIO device. Okay, so there's a lot of errors that were caused by that issue. Okay, so let's see what this produces. It's quite possible this should fail in some other way. No, didn't fail. Maybe something didn't get compiled. Let's see. Yeah. Oh, right. Okay. So I need to add also this device driver for the MCP chip to my device tree. No, sorry, not to the device tree, but to the linking. Let's see. Like this. I can probably automate this process entirely. But for now, I'll just do like this: mcp2317 co. So this will compile the driver into the firmware, and then we'll make and flash, and see if we get the driver. So, did we get the driver? No, we didn't. So it's not there. Let's see. Of course it's not there, because I haven't added it to the compilation. I need to add it to libfirmware. MCP, let's see, there. So I need to add it to the list of files that are going to be compiled, of course. And now I should get many more errors. Yep. So we need to include the SPI. GPIO. Initialization makes pointer from integer. Outcast. Unknown name console T. Yeah, of course, we need to also include the console. SPI find by ref. Find from ref, find by ref. I think that's a better name for it. SPI H. Find by ref or find from ref? Yeah, find by ref, I guess. I think it's the same thing with the GPIO. Find by ref. Yeah. Find by ref. Implicit declaration of function GPIO init. Right, it's GPIO device init. And GPIO register. Yeah, maybe like GPIO device register. Yep. And console find by ref. That's also something that needs to be updated, I think. If we even have that function, I don't think we have. So GPIO, I can copy it from the GPIO. Console find by ref. T. One. Let's see. And then console. Same method. Find by node, find by ref. mcp ops undeclared, which is it should be declared here. mcp2317 ops. 2317 ops. Oh, MCP, not MPC. MCP. S and printf. Size of name. Column declared. Console reset pin unused. save all the variables there, and let's see if this compiles. Nope. Back to debugging. mcp2317. Does this match our device tree? mcp2317. Oh, I see. Okay. Yeah. I need to add a dependency on this make file where I specify the drivers that get included because this needs to also recompile or relink the firmware properly. Let's see what failed there. I'm going to put it back to one line. Oh, I see. Could it be this? No? See, maybe it works now. So all of the packages, all of the libraries that are part of the build process, they're buildable for any system, any Linux system, or at least they should be. So, for example, libfirmware can compile as a Linux process, where the most necessary interfaces are emulated on Linux. So you get a version, like you get a actual free RTOS port, or you can have the thread library just linked to the pthread library, so you can get threads as well. So it's kind of like a user mode firmware, with as much of the code as possible shared between the two firmwares. So this successfully flashed. Let's see if this. Yes, it gives us ready. So we have the driver loaded. We have two chips, so we see that line twice, and now we should be able to run the command. Nothing to do. Great. So next step is now to actually talk to the chip and get a register dump, for example. So that is what I'm going to do. I'm going to do like this. And what we want to do now is basically write a small function that will allow me to test the interface to the chip before I then also bind this chip to some other driver which will toggle the individual GPIO pins on this chip. And for this we will do we'll use the command. We also need the musics here, so struct let's see, thread mutex. Actually, struct mutex. And this lock will be used this lock will be used in the public functions such as write pin, read pin, and also the command, because the command is always running from a different thread, and also write pin and read pin will be callable from different drivers, so they can in theory run from different threads as well. So that's the only thing here we need to worry about. So let's see. Now I'm gonna add some code that will actually write to the SPI. Let's see. RC equals 1. And Mr. CMP RB1 is equal to dump regs. And this will be our function that will dump the registers. This will let's see. So we'll look at the datasheet. So I'm not entirely sure what bank A and bank B means right now. Two tables shall register mapping with the two bank bit values. Okay. So there should be a register that sets the bank, I suppose. and there are slightly over 16 registers. So we can run it in a loop actually, like this. So let's have value mcp2317 read reg self reg just self reg, and then this will run in a loop. C less than 0x16. C++. I'm going to print this as a hex number and the value as well. So 02x. Reg value. And then, actually this will be the reg. Just like this. Reg. And this will set the GPIO pin, actually GPIO pin reset. Can we do that? Yeah, GPIO pin reset, self GPIO, self CS pin. So see how simple this becomes. And then we'll set the pin when we are done, and we will do an SPI transfer. So SPI, let's see, if actually int ret equals SPI transfer, SPI tx rx len timeout. So transmission will be I think we have to send the address and also the read-write bit. So we have address that's set to 0 in this case. We can see it from the schematic. We're setting the address to 0. So all of the A bits are 0. And read-write is 0. And this is... Actually, no. We have to check the SPI interface here. So can we see... Is it read-write? So when that bit is 1, does that mean we are reading or writing? There we go. So 0 is write, 1 is read. So we're going to set that to 1, so it's going to be 4, 1. So 0x41, and then register address, and in case of the SPI, we'll have register address, and then do I need to toggle the CS pin between the command and the readout? I wonder if I have to. Most probably not, but it's still something I would have to look up, I think. Okay, I'll just try reading out the registers without toggling the CS pin between the command. So registers are 8-bit long. It said something about 16-bit. Where did it say about 16-bit? 16-bit. No? Okay, I'll give it a go and I'll see if this works. So we have a SPI transfer, and then we have TX RX. Timeout, mcp2317, timeout. Right. And if red is, let's see, actually SPI would probably never, it wouldn't time out unless there is something wrong with the SPI driver. So if it's 0, then return E timeout. Return red. No, actually, if red less than 0, then I'll just dump the message to console. And this, by the way, should probably be the name of the instance of the chip. Let's see. Read reg, and let's see if this compiles. Oh, of course. What am I doing? So, let's make this a char TX. This will be the stuff we're going to be sending. It's going to be 0x41, and then followed by the register address, and then followed by a 0 byte. And char RX is going to be... Can I do that? I should be able to do that. Yes, I could do that. And timeout as well. Needs to be defined. Let's make this 100 milliseconds. Completely arbitrary value. Negative integer equals converted to unsigned. Yeah. I'll just ignore any errors here for now. And we'll return RX 012. and this will just be the let's see, struct self undeclared. Why is that? Oh, in the CMD function, of course. So this was here. Yeah, here we need to have struct mcp2317 self would be struct mcp2317 user ptr. So now we have the user pointer set to the actual instance of the driver. Let's try this. mcp2317.1 dump regs. Nope. So argv0 is supposed to be the name of the command. I was just checking if that was the case. And of course this needs to be equal to 0, in which case the strings match. And else console printf con invalid option. Okay. And there is no transfer at the moment. So something is not properly working. I'm going to check this with the scope. Let's see. So CS is pin 11. Let's see where it is. GPX CS. It's the 4th pin from the edge. And that pin is high. I really need to implement some kind of, let's see, yeah. I need to implement some history into this console. Okay. So, let's see. So there is no activity on this pin. So for some reason it's not. It doesn't appear that the CS pin is being toggled correctly. But there is data being read or SPI, so it's maybe just maybe it will actually work if I just make sure that the CS pin is toggled correctly. Let's actually make this an int and check whether it's actually a valid value. So it's going to be -1 by default, and here just print some info. SPI 3 control pins, GPIOs, GPIO-G, pin 15. And I think it could be that in the GPIO driver. Let's check. I'm going to check the GPIO driver and see if I'm enabling that GPIO-G. So currently I have just some code that enables all of the GPIOs. Yeah, GPIO-G should be enabled. Okay. So checking a bit more. GPIO-G. So 15 was GPX. Yes. And 3 was GPIO. And the reset pin, is that actually is the reset pin active low or active high? Active low. Reset is on the other side. And it is actually low, which is undesirable. So let's bring the chip out of reset and see if that works. GPIO set. GPIO self reset. Okay. Yeah, it's working. So all I have to do is just bring the chip out of reset, and this looks perfect. This is exactly according to the datasheet. So I'm pretty sure that it's actually reading the actual registers. So we are reading with bank 0, which is I assume is the default. And the next step is to implement the functionality that will configure each pin to be either input or output, and to do that from the device tree. So that's it. That's it for this video, and thanks for watching. I hope you learned something.